Greetings everyone. Welcome back to Multivariable Calculus. We're continuing to talk about the 3D graphing system that we're going to be using a lot throughout this semester or course series of lectures. Okay, so surfaces in space. We just got through talking about lines and planes, and remember we talked about how if something's going to be a curve in 3D space, you have to use parametric equations. But if something's going to be a surface in space, like a plane, then you could just use the equations again that involve x, y, and z, or one, two, or all three of those variables. Okay? So this section is designed just to give you an idea of some of the shapes that can come up when you invoke some of our most common operations. Okay? Before you do this also, I strongly advise that you refresh yourself on conic sections. This section is heavily reliant on the knowledge of the existence of the circle, ellipse, parabola, hyperbola, and we'll be doing combinations of those. So if you're not up on your conic sections, then you may want to pause, go run over and look up a few quick facts about those, or just refresh your brain on them. Okay? All right, so surfaces in space. Basically, we'll be doing something very similar to what we were doing when we were graphing planes in the last video. Okay? So we'll be doing a lot of coordinate plane traces. Remember we talked about the trace of something in the XY plane, or in the YZ plane, or in the XZ plane, right? We'll be doing a lot of that, but it may not necessarily have to be on one of the coordinate planes. We can also do it at other values if our graph is really just lacking in some dimension. Ha, pun. Okay? So as we get the few examples, you'll get the idea. So I want to show you all the possibilities in this first scene here, and then we're just going to work 6 examples for this section. Okay? So first, cylindrical surfaces. Now, I'm using the word cylinder and cylindrical, those words, very loosely here. When you hear the word cylinder, I know you think something that's in the shape of a can, right? Like the shape of the inside of a Coke can or a soup can. That's a cylinder. Yes, of one kind. Okay? The idea of a cylinder in our 3D space is any shape that is the same cross-section along any parallel line. Okay? So in our case, a cylinder is going to happen whenever we're missing one of the variables in our equation. So if I have an equation with just x and y, for example, then z will be the cylinder dimension. In other words, it'll just be copying the shape over and over again along the z-axis. Or if I have an equation with just x and z, then it would be a cylinder shape along the y-axis, or parallel with the y-axis. And the shape isn't always circular. The shape is determined by the equation that you have with the other two variables. So you can have parabolic cylinders, basically parabolas that are stretched over a parallel line, if you will. Planes themselves are cylinders. Imagine a line, and then you're just pulling that line along a sheet, right? That's a plane as a type of cylinder. Or you could have something as complicated as a sinusoidal cylinder, right? Imagine a sine wave, right? And then that sine wave coming out at you along a parallel line, right? As long as you can slice a cross-section along that parallel extruding, and it's the same cross-section over and over again, then that's what we're calling a cylinder, okay? And yes, it did take me a little while to draw that, and I'm a little proud of it. Okay, next, something that you've probably seen before and just haven't dealt with in a while, surfaces of revolution. We did a lot of these things in Calc 1 where you're finding the volume of shapes of revolution, right? Or we found the surface area of shapes of revolution, okay? One of the things that we'll be dealing with later in this semester is that we can do all of those same calculations in 3 space a lot easier than the way we were doing them in Calculus 1, okay? So having these things as equations that we can deal with, and then later on also functions that we can handle, okay? It makes it very useful. So if you, for example, want to rotate something around the x-axis, so I have some shape and the x-axis is coming out at you, you know, could rotate it around this way. Basically, you have y squared plus z squared, and you should recognize that as being a circle between y and z, and it's equal to some function of x that's been squared, okay? So that's basically a circle equation. Y squared plus z squared equals radius squared. And as the x changes, the radius changes, but it keeps that same generic circular pattern for the shape, right? Or if you want to rotate something around the z-axis, same idea, but your circle would be with x and y. So you have x squared and y squared. And your radius is some function of z, so that you'll have your shape in x and y, right? Some graph on your xy plane, and then the higher you raise z, the more of the shape you'll get, and it'll go around and around the z-axis there. So those are some of the generic shape ideas that can happen with just different equations that we have out there. Next, the quadric surfaces. This is where your conic sections come in. This is basically a 3-dimensional extension of your conic sections, okay? So your conic sections were all the things that had ax squared, by squared, anything with the dxy term, gx, hy, and then the n term, right? Well, now that we're in 3 dimensions, you can have all of the things involving z. So z squared, y and z, x with z, z by itself type of stuff, okay? So you have more possible terms, and that gives us more combinations of shapes dealing with multiple conic sections at once, okay? So it's going to be really important talking about these traces. You're going to have different conic sections as different traces, and they'll be all combined to make interesting shapes, okay? The simplest one, the ellipsoid. Imagine 3 ellipses, right? One flat on the floor, one standing up like the Z, and one doing side to side like this, right? And so you basically get a ball-ish kind of shape. Some people akin this shape to maybe like a football. You could also call it a sphere, a basketball, but to be a sphere, the A, B, and C have to be the same number, because remember, a sphere has the same radius in all directions. But that's basically a generalized sphere, right? Okay? An elliptic cone happens when one of your squares is negative and the other 2 are positive, and there are no number terms. It's equal to 0. So the equal 0 part brings it down to a point at the center, okay? So if you have no numbers and one of your squares is negative, you're going to have some sort of cone shape. Elliptic paraboloid. Well, as you can see, I have an ellipse in one slice, and then I've got parabolas going left and right and in and out, right? I've got basically a cup. It's elliptical. It doesn't have to be circular, right? That's why it's an elliptic paraboloid. If A and B are the same, then you'll have a circular paraboloid, okay? But all of these cross sections are going to be the ellipses, and then the standing cross sections in both directions, left, right, and in, out, are going to be parabolas that give you basically that cup shape, a parabola rotated around basically, right? So if A and B are the same, really what you're getting is something that's been a rotated shape, right? Okay, next, a hyperbolic paraboloid, not an elliptic one, a hyperbolic one. So look, there's parabolas, right, on one of the cross sections here this way, right? And that goes all the way across, but it's not a cylinder. It's not the parabola going straight across. It's more like a parabola rainbow like this. The parabola is sort of bent like this because you can have a parabola in this way as well. And it's really not two different things. It's what's happening is the parabolas are happening at different times, right? The Y parabola might be at one time, and then as it gets closer to the center, it'll switch to an X parabola. So you can imagine two parabolas meeting at different, locations like that, right? And it makes sort of a saddle looking point in the middle. But if you do a cross section across the pieces, you'll get hyperbolas, you see? If I slice along the Z here, I can get two separate pieces because the two sides are separate, and it would be in the shape of a hyperbola from in and out or from left to right. Okay? So a hyperbolic paraboloid happens when one of your variables is not squared, okay? And the other two that are squared, you have one positive and one negative. Okay, now keep in mind on all of these, whenever I'm writing Z, X, and Y, those can be maneuvered around, and what will happen is you'll have your shape in all different orientations, okay? The shape won't be changed unless you change the number parts, but if you swap around the variables, you can have, an elliptic paraboloid that's up, or you can have one that's out, or you can have one that's coming this way towards you, right? It just depends on the arrangement of the letters. And then you have hyperboloids of 1 and 2 sheets, okay? So hyperboloids, of course, like hyperbola, if it's of one sheet, then you can just imagine a hyperbola that's been rotated around, right? A hyperbola that's rotated around a central piece. This one has the Z as the central axis that's being rotated around. And if you don't have the number there, it basically becomes one of these, right? So right here for this one, what you end up with is kind of like a rotated solid where the hyperbola is the thing that's been rotated. So you have a hyperbola in two different dimensions and then a circle or an ellipse in the other, okay? And then the one of 2 sheets just means that now that 2 of your variables are negative instead of just one of them being negative, and when the squares happen. And side note, what's the difference between having 2 positives and 2 negatives? Nothing. But what's different is these 2 are both positive and this is 1 negative when the number over here is positive. See, the number over here is positive? That's the determining factor. That number on the side needs to be positive because we're adding up a bunch of squares, right? Okay? So you need to think about that for a second. If these 2 are negative, right, then it's a 2 sheets because I have 2 negatives, but it has to be positive on that side to make that work. Okay? So I get the 2 sheets because I have 2 variables that have axes that can't be done, that can't be intersected, right, without a shift or whatever. And basically, it's like a hyperbola that's been rotated by itself, like this way. Instead of a hyperbola like this that's been rotated and made a full circle, imagine a hyperbola that is already, like this and is rotated just around itself. So you get these 2 pieces here, okay? And again, the only way you can tell the difference is do you have 1 square that's negative or 2 squares that are negative when you're in these standard forms, okay? Keep in mind that these are very just generic approaches to these. The divisions by the a squared and the b squared can have different effects and can have different implications and things, but typically it's best not to just go through and memorize all of these things and what does a do, what does b do, and things like that, unless you're really going to study one of these shapes in depth. Okay? If you're not going to study it and we're just going to do like what we're doing now, we're just going to try and graph a few just to get the good idea, then just keep in mind in general what shapes can happen And then whenever you approach one of these to graph it, we'll just take it one piece at a time using the traces like I was talking about, okay? So just keep all of these shapes in mind, and let's go see some examples. Let's graph some examples. Y equals 4 minus z cubed. Okay, so the first thing that I like to imagine is, what would this look like if it were only two-dimensional? Because I only see two variables, right? Automatically you should be seeing the x is missing, right? And that should tell you, oh, this is one of those cylinder type of things. Because if the x is missing, that means it's going to be parallel to the x-axis, and x isn't going to have really anything to do with the shape at all. Okay, it's just y and z that are participating in this equation. Okay, so if I were to do a graph like this and put y here and put z here, let's say, in two dimensions, right? If I were to do something like this, what shape would this be, right? You need to ask yourself that. Well, z cubed, right? That's your cubic shape, the swirly thing. It's been reflected and it's been shifted up 4. So we would have something that would look along the lines of this, right? That's a relationship between y and z. With given where y is, it's acting kind of like an output there. A lot of times in 3D, we're going to want to have z by itself. But for now, I mean, just the way it's written, in 2 dimensions, I would expect it to look something like this, right? Where this is the positive y-axis, and this is the positive z-axis. But look at the way ours is oriented here. The positive z-axis is here. The positive y-axis is here, right? So it's almost like I'm looking from the back and rotated weird on this one, right? So start by rotating it this way, okay? I'm going to rotate it this way in my mind so that now z is here and y is here. Notice I have the positive y-axis. All I did was rotate this thing, okay? So it's not the normal orientation. Keep reminding yourself that here, what I'm doing here. And so what's happened so far is this, right? Where this point right here is at 4 on the y-axis. Okay? And then normally we would flip it around, right? So then if I flip so that z is here and now y is here, and the positive y is going that way, then we're getting the shape that looks like this. Okay? It's the same thing. I've just graphed it 3 different ways with different orientations of the z and y axis. Okay? Now it looks a lot more like the way we have our grid set up over here, and you just have to pretend that the x is coming out at us, right? Because x isn't a part of this one, so I'm just going to extrude it parallel to the x there. Okay? So let's start by graphing the cross-sectional shape here. Let's see. So it's going to hit y at around 4. Okay? So I'm going to count 4 here. Okay? And then it's going to hit the z axis whenever y is 0. That's going to be the cube root of 4. Something, you know, not that special. Right? The cube root of 8 would be 2. So the cube root of 4 is going to be less than 2, but bigger than 1, right? So it'll be somewhere in here, in this region. And what's going on is I'm going to have the shape going backward along the y-axis, you know, something like this. And it's coming down, and it's going to hit the y = 4 spot here, like it should. And it's going to do the cubic swirl thing, right? And now this part is underneath the XY plane right here. It's coming down. Let me straighten this out a little bit. Like that. Okay? Now, what I've drawn is the YZ trace, right? This is in the YZ plane. Okay? I know I'm not exactly the best at getting it to line up there. This could probably go a little bit better this way. You have to think of graphing as a process, right? Always doing a little bit of fine tuning here and there. Okay, so now, since I know that this is a cylinder and this is the cross-sectional shape, all I need to do is bring it along parallel with the x-axis, right? So I'll try to find a way. In this case, I'm going to put the ruler on one side on the x-axis, and I'm going to line the ruler up the tip right here with my graph, and I'm just going to draw a few, you know, lines here for that, like that, and that, and I'm going to try and keep it going, right? Now, of course, if you're going to do this with a straight edge, what you may just want to do is just put a couple of marks to continuously line it up until you get to the spot that you really want, which in this case, I'm trying to get to that center point there. And just keep drawing it there, right? And then I'll do something else similar further down here, trying to keep it parallel. And of course, it's not just in one direction, right? It's not just the band going this way, one direction. It's also the other direction as well, right? So this has to connect up here. All right. And then let's see, if I pick a spot like right here, right? Then I'll have the same shape. It'll be coming up and out like that, and then down and around like that. Ew, that's horrible. See, like I told you, it's a process. That's a little bit more like it right there. Right? And if you pick several other points, it's fine, right? Ugh. That's a bit better. Okay, so in other words, if you do enough of these, you'll get the general idea of what this shape is supposed to be. And of course, this thing keeps going in this direction as well, completely parallel to the x-axis that way as well, and this way. So what you have is a cubic looking surface, right? It's completely parallel with the x-axis, and it just does a little cubic swirl down into your y-axis like that. Okay? All right. Next, take a look at x squared plus y squared equals e to the 2z, right? So this one should scream out shape of rotation to you. I see the x squared plus y squared, that's something that looks kind of like a circle. And then I see something else squared over here. E to the 2z is also e to the z squared. So you could actually rewrite it like this if it helps you. Okay? So if you want to do the traces, like the xz trace, that's basically just letting y be 0. And what I would get is x equals e to the z. Okay? And then the yz trace would be y equals e to the z if I let x be 0. So you can see why this would be a shape of rotation. X and y have the exact same trace with z as they do with each other, right? Or not with each other, but they have the same exact trace to z, the same as each other, right? Now, of course, the xy trace, if you let z be 0, right here, if z is 0, you get 1, right? And that's just a circle. That makes sense, right? So what I've got is some shape being rotated around the z-axis, okay? So the question is, what shape is that? Y equals e to the z is a very specific shape. X equals e to the z, whichever one you want to focus in on, is a very specific shape, right? If I were to put the x-axis here and the z-axis here, or the y-axis and z-axis, whichever one you want to deal with, okay? Then you have to remember x is sort of looking like the output here, just like this one did over here. You're going to have to, in your mind, do a little bit of rotating. Or if you would rather, you can also solve this. But you got to be careful with just solving sometimes. Sometimes when you solve things, the methods that we use for that, you either gain or lose pieces with pluses and minuses and all sorts of other traps. Okay? But basically the shape that you're going to get is the LN shape here. It's going to look like this. Okay? Like that. So as x approaches 0, right, e to the z should become undefined, right? And as z gets negative, right, x should get smaller. And that's definitely happening there. Okay? If you're still not sure, then graph it the other way first and see that it makes sense to you. So in other words, if I had x here and z here, which is much like the way you're accustomed to graphing something in this orientation, right? Then e to the z would be like this, right? It would be like this. Be a normal exponential curve, goes through x equals 1 there. And just notice that this is the same shape. I've just done a flip here in my orientation. And it would be the same thing as the trace with the y. This would just be the y-axis instead. Okay? And then, of course, all of my x and y relationships should be circular. So this one's not as difficult to graph as this one, I would think, because all I'm doing is I'm going to draw a trace for each of these two pieces and then just make sure to connect them up with circles, right? So for the x-axis here, I'll just be drawing this exponential type of curve here where it goes through x equals 1 and then approaches the negative z-axis there, right? And then y would have the same sort of thing. Like so. And then you have to imagine these things going around in circles, right? So I would have something like this, like this. And then in the back, you'd have to imagine that this thing keeps doing this. So it keeps going down toward the center like that. And then, of course, since this is in the back, you could say, oh, this is dashed or whatever. But it's basically going to just keep doing that same thing. It's going to keep going down into the center like that. And then of course you should have some in the front right here doing the same thing. You know, it's going to come down from the front and go down in front like this as well. Like that. Okay? So that's just a graph of revolution. It helps to recognize the traces. And if you get down here, of course, don't forget you are still getting circles in X and Y, right? The back side should probably be dashed. The front side would be solid. And then just the further down you go, the smaller the circles will get. Like that. Okay? Now, of course, my hideous drawing here is nothing compared to what GeoGebra can do. So go take a look at these two graphs for real. All right, these first two examples here, I had to rewrite the equations in the form where Z was solved for before GeoGebra would recognize them in this form. I could also have done the parametric form, but in this case, the Z equals form worked out fine where you can see. The first one was the equation where y equals 4 minus z cubed, right? I just solved for z. And as you can see, it's the cubic shape as we guessed. And it's been, extruded like a cylinder. It's been stretched out. And it's parallel with the x-axis, right? It's just a cube shape and parallel with the x-axis there. Okay, and then the other shape was the x squared plus y squared equals e to the 2z. And one thing I forgot to mention in the lecture, the trace on the xz and the yz plane, the xz trace and the yz trace, I only drew half. We should have done the plus and the minus side, which would have given you the idea that it was also looping around. But take a look. See, if you do like the YZ trace right here, you can see that you should actually have one of those exponential curves on each side. I just rushed through it too much is all. And then same thing for the XZ plane, right? You can see that we should have one on each side. But what's basically happening is exactly like we described. It's that one curve, the e to the 2z, or the e to the z curve. It's the exponential curve, and it's just being revolved around the z-axis. More graphing examples. Yes. Let's look at this one. I have a positive x squared, y squared, and z squared, and that's it. So it's got to be an ellipsoid, but it's in the wrong format. I need to have an equals 1 on that other side. So I'm going to divide everything by 36, right? So that's going to give me x squared over 1. 9 over 36 reduces to over 4. And then 4 over 36 reduces to over 9. And now it's equal to 1. Okay? So then you need to think about the traces again, right? Say, for example, I want to do the XY trace, right? The XY trace is going to be x squared plus y squared over 4 equals 1. Well, this isn't called an ellipsoid for nothing. That's an ellipse, right? Where the x-axis has a 1 in either direction from the center, and the y-axis has a 2 distance from either direction, right? And you'll notice that all of the other traces fall into that same pattern, right? The YZ trace, right? That's going to be y squared over 4 plus z squared over 9 equals 1, and so on and so on, right? Okay, so let's start drawing a few of these things. The XY trace, and then let's do the XY trace first. So I have an ellipse, and it's centered at the origin. You'll notice they're all centered at the origin. I didn't have any singular x, y, or z terms to have to complete the square on or do any of the shifting here, right? So I only have to worry about being centered at the origin, and then the x distance is 1. So you can imagine that it would be right here and right here on either side of the x-axis like that. And then the y is 2. So that's here and here. So I'm looking at the back end here, and then the front end like this, right? Okay, so that's in the xy plane, and it's an ellipse. The yz trace, y has a distance of 2, which it already does, and z has a distance of 3. 1, 2, 3 is here, and 1, 2, 3 down the z-axis is here. So we're looking at z going down to y like this, and then coming back around to itself here. Z is going to come around to y-axis here, and then it's going to go a little bit behind, and then it's going to come out in the front again here. Well, you can guess where the last, now it's a little better. You can guess where the last ellipse is going to be, right? I've already got the points written in. It's going to have to go with the xz trace, which is going to have x with a 1 and z with a 3 again, right? Let's do this one in another color so you can see the difference here. It's going to go like this. It's going to hit down there, and then this is going to be behind it right here. Like that. Dash it up right there. Okay, so it looks kind of like an upward standing football, right? Because Z had the biggest contribution component there. Okay, and that's it. That's the ellipsoid for this one. Works a lot like a normal ellipse, right? All right, next example. Z equals y squared minus x squared. And even if you can't think of what this should be when you're looking at it, like, oh, the name of it just slips my mind, you can still get the traces out of it and then try to take a look at what shapes you're going to have to puzzle piece together. This is one of the more intricate ones to have to piece together because of the way things keep switching direction. Okay? It's a hyperbolic paraboloid, and that means that what you're going to have is some parabolas that meet up in different directions, and then if you slice it another way, you should have some hyperbolas. This is the one that gives you that saddle shape, right? Okay, so let's look at the traces first. If I do the zy trace, in other words, x is 0, right? I have z equals y squared. Yeah? So with z and y, I'm getting something that's upward facing. Here's z, here's y. I should get a parabola like this for the zy trace. Okay, what about the zx trace? Here's z, here's x. The zx trace is z equals negative x squared, right? Well, that's still a parabola, but notice it's downward facing, like this. Okay? So let's see if this makes sense when we try to draw it on the graph over here. The zy trace, let me get a little bit more y-axis here to sort of get a good development. Let's get some y-axis over here. right? And we'll get a little bit more of an x-axis too while we're at it. A little bit more x-axis. Good. Okay. So then zy, right, is an upward facing parabola at the plane, at the origin there. So I can imagine the zy trace being like this. Something like that. So it's in the zy plane there, right? Okay. But then the zx trace is a parabola that's facing downward. So in this plane right here, I need to imagine a parabola facing downward like this, right? And then this kind of, I'm sort of getting the feeling like maybe this would be behind it over there, right? So you've got these two parabolas that are meeting up like this, right? So you kind of got to look at it and be like, well, I'm not sure exactly how that's going to go. So you can actually venture away from the traces a little bit. Those are just some good beginning points. What if I were to let y be a number other than 0, right? So instead of calling it the zx trace, I could call it y equals 1, let's say. Because that's what's happening, right? And in that case, I have z equals 1 minus x squared, which is the same exact shape, but what's happened to it? It just gets shifted up by 1, right? And then what happens if I plug in y equals 2, right? At y equals 2, I would get z equals 4 minus x squared. So it's basically getting shifted up again. The further I move along the y-axis, the further up this thing is going to shift. So y equals 1 is going to be about, right here-ish, about right here. And so at that point, I'm going to have a parabola that's been shifted up like that. Okay? But these two are connected parallel to the y-axis here, right? And then again, at 2, it should be up at 4. So I should have another parabola sort of doing this, right? And then what do you think happens on the other side? Look at the way these are meeting up. If I plug in y equals a negative number, the square just gets rid of it again. So I'm still going to have these parabolas going over here, right? That are just going around the other side of that one there. Okay. Next, what happens if I let x be a number, right? We need to think of that also. What happens if I let x be a number, like x equals 1? I get z equals y squared minus 1, right? So again, I would have this y parabola here that I've been using, and it would come to x equals 1. It would come down the x-axis some, but then this is the same shape but shifted down a little bit. That should start to make sense to you, because look, if I graph, I'll do it in a different color here, something that's down, like I go 1 in the x, but down, right, to here. And then the shape is going to start to meet up like this. Like that, right? And it's meeting up with these other curves here and here. So you should start to see it a little bit now. It's got this saddle piece in the middle there, and it's riding high up on this side. Well, what about the xz value, the xy trace? If I let z be 0, okay, the xy trace, it's not going to be as informative, because basically I'm just getting x squared equals y squared. And really, pretty much, it's just the 0 point in the middle there, right? It's not helping me a whole lot. It's just the lines where x equals y and y equals x. But again, it's not totally helping me. I'm having some pieces go this way and that way. That's not helping me a lot. But it will look more familiar to you if you let z actually take on a different value than just doing the z equals 0 for the trace, right? So in other words, let z equal 1. I would have 1 equals y squared minus x squared. There's one of those hyperbolas that's in the name. It's a hyperbolic paraboloid, right? Okay, we've been drawing parabolas up until this point to get the shapes in there. But now we can start drawing a hyperbola. When z equals 1, that's like a level right here that's just above the xy plane. I should have the hyperbola that has its center at 0, 0, but both x and y have that distance away of 1, and the x-axis is not touched. So like if this is the x-axis here, it's the hyperbola that's on either side of the x-axis not touching it, right? So then at z equals 1, you know, you imagine something like this. You're going to get a hyperbola that's going to look like this. Here and here. Like that. Okay? So no, it's not exactly doing it justice, but hopefully you can see it a little bit. What we're getting is this surface here, right? And this surface here. And it's riding along the same, along the back here, right? Down this way, like this. And you're getting that saddle in the middle. Okay, so like I said, this is one of the more intricate ones to draw because of all the different switches in direction. But hopefully you're seeing that it's kind of like a Pringle chip. It has a hyperbola in one way, right? And then parabolas that meet up differently. So it's kind of like I'm hanging parabolas along another parabola here, right? I have the one big parabola going along here, and I was hanging these other parabolas along that shape. Yeah. And then what really ties it all together, like I said, is using the hyperbolas over here. These should be hyperbolas getting wider and wider as you go down. Right there, right there. And then these are going to be parabolas as they go up. And then as you get to the bottom over here, the hyperbolas underneath here switch direction to this way. Like way underneath here, they switch to this way. Right? Because if you let z be -1, then you have -1 equals y squared minus x squared. But to make that a true hyperbola, you have to have 1 on this side, which means I would have x squared minus y squared. So when you go below the xy plane here, the hyperbolas don't go this way anymore. They go this way now, right? Because I'm going to have a shape that goes up like this along the y-axis, but then it's also going to go down this way and this way along the x-axis, right? Like a saddle. It's high up on the y-axis side, and then it dumps down on the x-axis side, like that. Okay? This one was okay, as you can see. I know I butchered that one pretty badly, but hopefully you got the idea from the traces. And let me show you what that one really looks like in GeoGebra, because it'll really hit it home for you. Okay? Go take a look.
Alright, so for these two examples, let's start with the ellipsoid. 36x squared plus 9y squared plus 4z squared equals 36. There it is. Looks kind of like an M&M, doesn't it? Alright, so this is a good shape to be able to see in a nice, efficient, concise spot like that, because it's, confined to this little region. But I also have the parametric form for you, so you can see the cross sections and grid lines on it, how it can be sliced up. Alright, and then next we have the hyperbolic paraboloid, z equals y squared minus x squared. here the sheet itself is very large and gets very large very quickly. So even if I zoom in, you see you can't hardly tell, but look, there's those two parabolic traces. Here's the ZY trace here that you can see, it's cleared out there, and then here's that ZX trace that we talked about, and they're completely perpendicular to each other. And then also you might remember the XY trace, we talked about how it was the two lines, right? You can see where it's intersecting the plane there. It looks like the two straight lines. You might be able to see this one and see the depth of it a bit better if I use the parametric form with the grid lines on it. So you can see it's the same shape, but you can actually see the cross section. You see the parabolas that keep getting lower and lower here as we go along the x-axis. There's a parabola, there's a parabola. And then vice versa, if we go along the y-axis, you can see the parabolas that are facing downward here, and you can see they move up as you come along the y-axis. And then you've got your hyperbolas, because you can have the cross-section that goes along laterally on the side of this, and then you'd have the other side over here. Right? You have the cross-sectional hyperbolas on either side here. Or if you go below the axis, you have the hyperbolas here to here. Right? The hyperbolas switch directions once you get below the XY plane there.
Let's finish up with a couple of more examples, and then you can see some more GeoGebra. Let's look at this one first. I've got x plus y squared plus z squared equals 2. Okay? To make this one look a little bit more like the pieces that we were seeing in the original menu there, what I'm going to do is I'm going to get x by itself. And typically when you have one non-squared variable, that's kind of what you want to do, like this. Okay? So then it may not look exactly like one of the formats from earlier, but you'll notice that you have a variable and it has the other two variables squared and the same sign as each other on the other side. So this is that elliptic paraboloid that we were talking about, okay? Except the extra 2 there has just shifted it some, right? And the fact that they're both negative here has reversed the direction of the opening, right? Okay, so x is the loner. So what you can expect is the x-axis should have had the cup going around it, right? Except we have the negatives on the two squares, so the cup is going to reverse, right? And it'll shift it 2 along the x-axis like that. Okay, let's look at it by doing the traces though. The xy trace is x equals 2 minus y squared by just letting z equal 0. And you'll notice that that's the parabola that would be facing downward, right? If x were the vertical axis, right, it would be facing downward in the y direction, okay? So towards the negative side of x, in other words, right? So here's my y-axis. I can expect this trace to be a parabola facing in the negative x direction. However, it's been shifted up by 2, right? So in other words, when y is 0, x is 2, so that's here. And notice when x is 0, y is going to be plus and minus square root of 2. So that's about 1.4-ish here, negative 1.4-ish there. Okay, so I've got this parabola going outward that way. Okay, in the plane. like that. Right? It's in the XY plane going outward that way. Then, if you do the XZ trace, right? Notice I get something extremely similar. It's just Z instead of Y. So you can use all of the same stuff, right? I'll have that particular trace, but it'll be between X and Z. So again, the Z will be pointing towards the negative X direction, right? The Z being squared means that it's the axis that will get hit twice at the 1.4 point and the negative 1.4 point. And again, it'll be going through the X equals 2 spot. And it'll be doing this, right? Like this. Okay. Now, what about the YZ trace? If I let X be 0, we'll just come back up to the original equation. If I let X be 0, then I've got Y squared plus Z squared equals 2, which is a circle, radius, square root of 2. And you've already seen that it should be this way, right? The square root of 2 was the number that I kept going around in all of the axes for the intercepts there. So here the YZ trace is this circle. This should be solid here. And then this should be solid here, right? And then this piece is going out this way like that. And again, circling up to here, circling around to here. But this circle is in the ZY plane. This circle should actually be going outside of it, like kind of misled there, more like that. And then this is the underneath right here. Whoops. Let me fix that really good right there. Really well. So this is going underneath, right? That's the underneath. And then I should have a circle coming up to here, coming down to here, and then around to there on that side there. Okay? And then of course I've got the pieces going this way. It should be an elliptical paraboloid. In fact, this one's even circular, right? And it's just the cup facing this way. And I got it all just by doing the traces, right? I have two parabola traces, two parabolic traces, and then they're connected by a circular trace, like that. So you can tell it's going to be the cup version, right? But it's facing in the negative X direction because of the way the Y and the Z both have the negatives on them. Okay? All right, and last one here. See if you can guess real quick which one it is, or maybe you've already looked at it a little bit. I have an X squared, a negative Y squared, and a negative Z squared, while the other side is a positive 1. It's a hyperboloid of 2 sheets, right? I've got 2 axes that should not be touched, the Y and the Z, because these aren't shifted, right? Again, there's no numbers inside with the squares, or there's no separate X and Y terms that I would have completed the square on, or anything like that. So it's still centered at the origin, okay? But it's going to be a hyperboloid of 2 sheets, and the only axis that can actually come into contact with the graph is the one that's positive, so that would be the x-axis, right? So here in my x-axis, that's the axis that I'm going to come into contact with, right? And think of it like a hyperbola. My x-axis is going to be going this way, so I can imagine a piece going towards the positive x, and then I can have another piece on the other side going towards the negative x. So I'm expecting something, you know, the double cup type of graph like this. Okay? So let's do the traces and see if that makes sense. The xy trace is going to be x squared minus y squared over 9 equals 1, which is a hyperbola that only touches the x-axis and has the box that you draw in between it, where x is a distance of 1 from the center and y is a distance of 3 from the center, which is, typically where you draw your asymptotes for your hyperbola and things like that. But let me just do my best. Right now, we're getting that x is 1 unit away, and that's actually the axis that it touches. So it's going to hit 1 and -1 there, right? And then it should be a hyperbola with a slope of 3 over 1. So it should come out this way 3 for every 1. So you're expecting an asymptote to go, something like this through the xy plane, right? Which means I would be expecting, let's see, if I did a box like that, I would be expecting my hyperbola to be sort of wide in the xy plane, kind of like this. Okay, so my xy parabola should be kind of wide there, like so. And then of course the other side the same way. I'm going to have something in the back that's coming up here and going out wide that way. So that's the xy trace. I have a hyperbola in the xy plane, right, where the y-axis is not intersected. It's centered at 0, 0, and the x distance is 1, right? So I've moved 1 on either side of the center. Okay? Don't need these dots on there. Next, the xz trace. When y is 0, I have x squared minus z squared equals 1, right? So again, that's a hyperbola, but it's a square hyperbola, right? It's one where the x and the z are equally dimensioned. And so I'll get a hyperbola still with x and z, but it'll be like this, right? The x will be facing this way, the other x will be facing this way, and it won't touch the z-axis. But it won't be as wide as this one because x and z are equally portioned with 1s. So if I actually were going to find, z equals 1, like, up here, and z equals -1 down here, I could try to space my box sort of like, let's see, here and here, like that. And then I could try to space it a little bit skinnier, like this, underneath, like that. And then of course this piece right here is actually in the back. So let me redraw that piece. Like so. Right? So you got to kind of imagine, let me see if I can make this a little bit thinner here. Not thinner, but more proportionate. Like it's coming out at us. And then the same thing on the other side. I still haven't done the other side of this hyperbola. The hyperbola between x and z should be a hyperbola standing up on either side like that, right? So I should be able to get the other xz hyperbola doing this. Like so. Okay. Now there is no YZ trace. How can I tell? We'll try to plug it in, right? If I try to do a YZ trace, okay, you're going to get negative y squared over 9 minus z squared equals 1. And that's just impossible, unless you're talking about imaginary numbers, because I can't square these and then have them both be negative and then yet end up with a positive 1. It's just not going to happen. And that's why you're seeing a big blank space in between these two cups for your hyperboloid of two sheets. you're getting your two cups facing away from each other with all this dead space in the middle, right? And it's because there isn't enough correct values, right? There's no correct values to make this true. So there is no YZ trace here. There's no way, it's not hitting the YZ plane. However, if I were to pick X values that were far enough away from the center, right, we'd start hitting graph. Well, when X equals 1, right, I would subtract 1 from both sides and I'd have this equals 0. Well, that means I get these 2 points. They're singular points. They're circles with radius of 0, or ellipses in this case, right? So if I pick an X value large enough, I could actually get not necessarily a trace, but it's what we call a level curve, like I've been doing with some of the other ones. For example, pick X equals plus n minus the square root of 2, because it happens at both, and when you square it, it's the same thing, right? What happens is I get 2 minus y squared minus z squared equals 1. And you can manipulate this by adding the y and z squareds over and subtracting the 1, so that I would get 1 equals, oh, I'm sorry, it's supposed to be over 9. Y squared over 9 plus z squared. Okay, so basically I'm getting a curve that fits on the equation. When x is plus and minus square root of 2, I'm getting something that's elliptical in y and z. And notice y stretches out a lot further than z does at these locations. Okay, so what we're getting is when x is, let's see, if this is 1, this is 2 right here. So at about right here-ish, right, 1.4-ish, I'm going to have an ellipse. Let's go parallel to the y-axis here. Parallel to the y-axis would put me here and here. And then parallel to the z would put me here and here. So this is what's happening. We're getting an ellipse. Whoops. Close. You can see where my skewedness of the hyperbola here is a little bit off. So it should be like this. Right? So you should be getting that. And of course, the larger I let x become, right, the larger this number on the other side would be, and I would have to divide and make the sizes of the variables larger. So the further away I get, I basically would keep getting these ellipses, right, that keep hitting down here, up to here, and then like that. And then the same thing's happening on the other side. I'm getting an ellipse here to here, and then underneath here, back up to here. And then the further out you go, the larger the ellipse has to be, like this. Like that, right? I didn't butcher that one quite as much, right? So you can see it's the 2-cup hyperboloid of 2 sheets, basically wrapped around the x-axis, but it's not circular, it's elliptical, because the y has a different skew than the z, has a different warping, right? Okay? So I hope this has given you a good place to start. These are skills that you need to practice, okay? If you're one of my students, I would have already given you a sheet that has this nice little grid that has the dots on it. Let me comment on that real quick. When you have one of these graphs and it has the dots on it, what you need to notice is that the dots work in parallel with the axes. So it won't look like rectangles, right? It'll give you the dots that are parallel to an axis in all the different directions. So I'll have dots going this way and I'll have dots going this way. And it'll look like a jumble of dots, but if you follow parallel to an axis, that's how you're supposed to use them, okay? So I know that I always give those out. If you're somebody just watching this, send me a comment. I don't mind sending you the file that has these nice graphs with the dots already on them. But bottom line, this is a skill that needs to be practiced. You can't just watch. I hope I've given you a good place to start. Go look at these in GeoGebra I'm about to show you, and thanks for watching.
Alright, so these last two graphs, let's take a look. X plus y squared plus z squared equals 2 is indeed the elliptical, or in this case circular, paraboloid going across the negative x-axis. As you can see, the x-axis is the red one there. It's pretty good to see here, but let me do a parametric form instead. Actually give some grid lines to it, like that. Notice it actually even gets some of the little curves in there, some of the cross sections that you would get if you were to slice into it. A bunch of parabolas in all the different directions. Okay. Next, the hyperboloid of two sheets. Right here again, you can see it's the double cup, basically going either direction of the x-axis as we planned out. And it's really wide in the y-axis, especially, as you can see. And just like the other one, it's easier if I do a parametric form that gives us a couple of little curves that splice into it. Right? You can see the cross sections of the curves that splice into them there for that. Okay?